Welcome back as we look at graphing our polynomial functions. Now think about what we can do to graph them. Our directions are for the next three problems determine the graph's end behavior. We know how to do that. The intercepts. We certainly know how to find x-intercepts and y-intercepts. And then we're going to look at symmetry, and then we're going to graph our problems. I'm going to ask you for one more thing when you graph, but we'll get to that as we work along. Now remember that intercepts are where x equals 0 or y equals 0, depending on which intercept we're working on. Now when we looked at zeros, we said those occurred where y was 0 and we found the x's. And we have done some equation solving where we have gotten some imaginary numbers. Those imaginary numbers are not intercepts though, because we're not graphing imaginary numbers on a real number plane. Okay, let's get busy with our equation then. Our first equation is f of x equals x cubed minus x squared minus x plus 2. All right, we're going to talk about end behavior first. Okay, it's of odd degree here. So that makes us jump to y equals x cubed graph. Think of it as our pattern. A positive lead coefficient here. Well, this has a positive lead coefficient. So it's going to have the same end behavior as y equals x cubed. It's going to rise to the right here and fall to the left. So it rises right and falls left. Next, we want the intercepts. So if I find the x-intercept or intercepts, I will let y equal 0. So I plug in 0 for y. 0 equals x cubed minus 2x squared minus x plus 2. And of course, the first thing I would like to happen is that I could factor this thing rather than have to take some other strategy to find our intercept here. And it looks like I can factor an x squared out of the first two terms. So x squared times x will give me my x cubed back, and x squared times negative 2 will give me my negative 2x squared back. Then when I look at the last two, oh me, I don't see a common factor. Oh, that's right, 1 is a common factor of anything. I can factor out a 1. Since this is negative before the x, I'm going to factor out negative 1. Negative 1 times x here gives me minus x back. And then I'm going to be really tricky here. I'm going to say if this doesn't match this, I'm in a whole bunch of trouble. So I'm going to write what I want it to be, and then I'm going to check it to see if that really worked. So negative 1 times x does give me the minus x back, and negative 1 times negative 2 does give me positive 2. So now that I have a common factor in both terms, I can go further. Remember, if I don't end up with a common factor at this point, I'm stuck. So I'm going to factor out my common factor of x minus 2. And I'm going to have to multiply by x squared to get all of this term back. And I'm going to have to multiply by minus 1 to get all of this term back. Let's check it now. Let's treat this as a clump. X minus 2 times x squared. Yep, that's what that is. X minus 2 times negative 1 is minus 1 times x minus 2. So it checks. Looking at this one right here, do you recognize difference of squares? We'll bring down our first factor like it is. We'll factor this into x plus 1 times x minus 1 since it's difference of squares. All right, so now letting each factor with an x equals 0, we end up with x equals 2, x equals -1, and x equals 1. Those are our 3 zeros. The answer we got when we plugged in 0 for y. That means we're going to graph 2, 0, -1, 0, and 1, 0. So that's what we'll graph to go with those zeros. All right, let's find our y-intercept next. To find our y-intercept, we'll let x be 0. Y-intercept, let x equal 0. And we get y equals 0 cubed minus 2 times 0 squared minus 0 plus 2, or y equals 2. So that's our y-intercept, and the ordered pair we're going to graph is 0, 2 to go with it. C, they want symmetry. To check for x, to check for y-axis, let's change that. To check for y-axis symmetry, we're going to use opposite of x in place of our x and see what happens. So let's erase here and get us a little workspace. In fact, we can erase all that too. So looking for symmetry, I'm going to say my new y equals opposite of x cubed minus 2 opposite of x squared minus an opposite of x plus 2. So my new y is, when I cube a negative x, I get negative x cubed. When I square a negative x, I get x squared times the -2, so that's -2x squared. Minus a minus is plus x plus 2. And now I look, is this polynomial the same as our f of x? Nope, it's not the same. It does not equal f of x. Therefore, we have no y-axis symmetry. Now, we'll check next for origin symmetry. All right, checking for origin, we're going to use opposite of x for x and opposite of y for our y. So let's erase and work on origin symmetry now. So we'll use opposite of y where we had f of x, and that's our new y. And we'll use opposite of x cubed minus 2 opposite of x squared minus opposite of x plus 2. So opposite of our new y equals minus x cubed minus 2x squared plus x plus 2. And now we want to get just a y over here rather than opposite of y. So we'll multiply both sides by -1, and that will give us y. So negative times negative is positive, so we have positive y. -1 times minus x cubed gives us positive x cubed. -1 times -2x squared is plus 2x squared. -1 times x is minus x. -1 times 2 is -2. Now we're going to ask the question, does our new y equal the old f of x? So I'm going to compare this and this. No, They are not alike, so that says no origin symmetry. So that means we have no symmetry because we've checked for both kinds. Next, we're going to use what we have to graph. And I have that written down so that when I go to our graph slide, we'll be able to graph what we have. So let's advance. We are going to graph 0, 2. We're going to graph 2, 0. We're going to graph 1, 0 and negative 1, 0. There's no symmetry. We know we're going to rise to the right and fall to the left in the end. So we'll just make ourselves a little note to remember that. Now let's think about graphing this thing. We've gotten our zeros, and that seems logical. We need zeros where it crosses the x-axis to figure out where to graph, and it's real easy to plug in 0 for x, and that's an easy point on the graph. But you know what? I do not know how steep to go up here. Do I go up like this, or do I go up like that? So I need to check my end behavior. Both pass the 0 here to the right and pass the last 0 here to the left. So for some extra points here to help me out, I'm going to get 2 points that are at the ends. In other words, one past the 0 on the right here is going to be x is 3. So I'm going to check x equals 3. And then I'm going to come over here just past this one, and I'll be at x equals negative 2. So I want to find the y value for x is 3 and x is negative 2. So let's erase these off our graph since they're not on it. And now, you know, I would like to know just how high the graph goes and just how low it goes when it makes that turn to come back up or down. So let's do our relative maximum and our relative minimum. Now, why do I say relative? That means in just a little chunk of the graph that I can pick out, I have a peak or I have a valley. It's not the overall maximum or the overall minimum if there is one. Instead, it's the maximum or minimum in a little chunk or interval of the graph. Well, to find that, we're going to have to use a calculator because we don't know calculus to find the maximum and minimum points. That's why a lot of books in college algebra level don't ask you to find the maximum or minimum point, but instead just suggest that you get halfway between your zeros and get a point. But with the calculator, we're going to find that maximum and minimum point. So let's go to our calculator here. And I feel real lazy since I've got to use the calculator anyway. Why don't I let it give me the 3 and the negative 2? So let's clear our y equals. Type in our new function, which is x cubed minus 2x to the second minus x plus 2. And let's look at its graph. I hope we have a good window. Ah, looks like a good window, all right, because I can see where it turns here and where it turns here. Now, thinking about that, I wonder if I see all the turns. Actually, I do. Since we have degree 3, we have at most 3 real zeros here. That means we have at most 3 minus 1 turns, or 2 turns. So if we see all the zeros and 2 turns for a cubic, we're okay. We know we're seeing what we need to see. All right, let's pinch in on this maximum. Let's pinch in on this minimum. I do maximum first just so I can remember what I've done. So second, calculate maximum. That's selection 4. And I'm going to pinch in, so I need to get a little to the left of my maximum, hit enter, a little to the right of that maximum in that little narrow part of the graph, click enter, Click enter again. And my maximum is negative 0.21524, so forth. We're going to round it to tenths because I don't think I can graph any closer than that anyway. So our maximum point is going to be negative 2/10 and 2.1 for y. All right, and I'll remember that so we can write it down in just a few minutes. And then second, calculate. Let's find our minimum point here. Selection 3. Go a little bit to the left of it. Maybe I better back up a little, make sure I'm to the left. Then skip on over to the right. Yeah, I've made the turn, enter. And now I've gotten 1.5 for the x and negative 6/10 for the y. We also said we wanted to find the values of 3 and negative 2 over here, so let's look at our table, second table, and let's back up. Oh, no, we've got it. Negative 2 is negative 12, and 3 is 8. All right, so let's go back to our graph and put in these values. For 3, we had a value of 8. For negative 2, we had negative 12. I think I'll do it in red like the other is, 8 and negative 12. For our maximum and minimum points, we had negative 2/10 and 2 1/10. We had 1.5 or 1 5/10 and negative 6/10 to graph. Now the reason I thought about leaving this in red is I need to know how steep to go up or down. I don't necessarily have to have any of these points on the graph. I do have to have my maximum or minimum on the graph. Well, my scale is going to take care of both of these y's, so I'm okay with a regular scale here. Let's get our 0 back on there a little bit better. So let's graph negative 2/10, 2.1, 2/10, barely over 2 right there. And then 1 1/2 right here, and negative 6/10, about right there. And then 3, 8. Can we get that on here? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. It's right up there. I'm probably not going to go that high, but I know I'll head toward that point. Negative 2, negative 12, here's negative 2. We're off the graph. So we know we're still going down without crossing negative 2 at this point. So as I draw my graph, I'm not going to let it cross x equals negative 2. I'm going to go up to the max, turn, come back down to the minimum, going through my zeros, and I'm going to head up toward that next point without actually getting there. And the graph goes on in both directions. In other words, the domain for a polynomial function is going to be every number for x or negative infinity to positive infinity, all reals. And we can use all reals for y also right here, where it goes up and up and up and down and down and down, which is not true of every polynomial function. If you'll think of y equals x squared, you'll know that we don't use every number for y every single time. All right, we'll continue graphing in the next session.